So, welcome to this lecture number 21, HVDC. Now, what is HVDC? It is a high voltage DC transmission. Now, you may ask me, when everything is being shifted to AC, why we are talking about anything direct current? Let me tell you, this HVDC was, or even direct current was gone forever, but in 50s, to be precise in 1954, it staged a spectacular comeback. So, first commercially used HVDC link, which was of 20 megawatt and 100 kV, was established, installed in 1954 from Sweden mainland to island of Gotland. 1970, as the power electronics progressed or electronics progressed, the Shockley effect 1960 and advent of transistors. So, valves slowly but surely got replaced by thyristor valves. So, 1970 thyristor valves replaced the valves based on mercury arc technique. You must have read mercury arc rectifier in your undergraduate. Biggest HVDC to date, that is 2003, is in Brazil, and the system is called Itaipu. Itaipu, it is popularly called Itaipu. Brazil is known for its contribution to energy. I told earlier on in this course that the biggest hydropower plant is also in Brazil on the river Amazon. It is 12,000 megawatt. Imagine we have only 1200 megawatt. Our biggest hydropower plant, that is Bhakra. It started in 56 and even in 2006 is now after 3 years, and it continues to be the biggest. The Brazil system is of 2 bipoles, 6300 megawatt and plus minus 300 kV. Now, what is DC transmission? Obviously, generation has to be AC, because DC generation is hardly there. Then why we have gone for DC? What was wrong in AC transmission, which is anyway predominantly most of the transmission is AC even today and will continue be so in future. Yet we are going for HVDC in a selective way to get certain advantages in certain situations, which I will explain you what are those situations. So, DC transmission effective it is an effective way of or means of improving system performance. It is complement to AC systems. We never want to replace AC by DC. In fact, we want peaceful coexistence of both simultaneously, exactly in the same way as we have non-conventional energy sources and conventional energy sources. Non-conventional energy sources are not competitor to conventional energy sources. We primarily mainly use renewable energy sources or non-conventional sources where it is not possible to use conventional energy sources. Even today, where do you use bullock cart? Where there is no rail line, where there is no road, where we can run the bus. So, interior, or if it is a waterways, we go by steamers, we go by boats even, and recently we are now proposing ferry to Bombay to Karachi, which used to run before 65, the first or second Pakistan, Indo-Pakistan war, if you consider 48 as the first war, Kashmir. Why we are going by ferry? Because there is no railway link, there is in between sea. So, in India, first HVDC line, world was 54, that was Sweden to Gotland, but in India the first HVDC line came from Rihan to Delhi, and this was plus minus 500 kV, 800 megawatt, about 15 years back, roughly 1990. Since then, we have had several HVDC applications. There is one at Chandrapur, a big HVDC station, one in Satpura, and I hope if you can be taken to one HVDC station to see it actually, I do not know whether it will materialize or not, whether even you will be able to go to the load dispatch center which is across the road, but my job is to tell you where you should go. So, this Rihan to Delhi line is continues to be our biggest HVDC line. Now, they want to connect still bigger north east to south, 2000 kilometer plus minus 600 kV and 2000 megawatt. Why? Because the northeast has potential, it can generate power, but there are no takers, it is not required there, unfortunately or fortunately, the way you look at it, but it is required in south. So, that line will go all the way from Assam to down south to Karnataka. Global HVDC transmission, which started with a modest 20 megawatt in 1954, is today 17.9 gigawatt. So, it is 1000 times. Suppose you assume this is also 20, this is also 20. So, from megawatt to gigawatt. Largest device rating so far is 5 kV, 3 kiloamps. See, device, this is there a simultaneous progress in power electronics also has helped in becoming, in making HVDC more and more attractive, more and more cheaper. Why we are going for these power electronic devices? Because of their availability in a bigger sizes, easier of control, yes, and cheaper. Highest transmission line voltage is plus minus 600 kV in the world, not in India alone, and growth is 2500 megawatt per year. Every year you have another 2500 megawatt available through HVDC throughout the world. It is not India, it is throughout the world. Yeah, that is one device.
Yes, sir. So we got IGBTs for even 65 kilowatts. 65 kilowatts, 2.5 kiloamps.
But there may be some problems while using for HVDC, that you can use for any other application. For HVDC it is not yet used. There are certain problems with the inverter and converter stations. So, its application is main important thing. For example, some patient can be given khichdi, some even cannot be given khichdi, only liquid diet because of the requirement. So, because of that perhaps it is limited to only that. How do you convert AC to DC? Because generation continues to be AC. So, what are the principles of converging the AC supply to DC supply? Converting two converter stations connected to each other by a DC cable or a DC overhead transmission line. Now, not all places you can use overhead transmission line. So, that point we have already discussed a lot while talk. That is why I did cable also one lecture or part of a lecture. So, we need to use cables, DC cables also. Do not think there are only AC cables. A typical arrangement of main components of an HVDC transmission line is shown in the figure, which is coming next. Now, these are the main components of a HVDC transmission. A typical arrangement does not mean it has to be exactly like this. So, this is just a typical arrangement. It depends on a particular local needs. This is a AC bus. After generation, you transformer, bring it to a particular voltage, and from here it comes to converter station, and converter station is so big. There is a control system, there is a converter, there is a filter, there is a AC filter, there is a shunt capacitors, SVS, any other reactive equipments such as synchronous condenser. Reactive power management you have already done. What is the one negative drawback of HVDC? Before we talk of positive thing, the negative drawback is, it cannot transmit any reactive power, unlike its counterpart or its elder brother HVAC, where you can very easily transmit reactive power, which is naturally available to you. Because when you connect synchronous generator to transmission line, whether you like it or not, along with PS, QS is also there. There is a Choli Daman Saath, as they call it. They are always together, like your shadow. Now, this case you cannot transmit anything, forget about a part. So, you don't only you have to prepare for any shortfall, but the whole total requirement you have to supply additionally, whether you supply locally, globally, by theft, by borrowing, by begging, that is a separate issue, but it has to be not through transmission line. That is the main point. This is one of the main drawbacks of HVDC lines. However, since we have another sources, so it is not that big a drawback that will deter you, that will force you not to adopt HVDC option.
Installation cost is also another.
Well, overall cost you have to compare, you have to see, it depends on requirement also. There are so many other factors, this is just one factor. I am going to talk about 20 factors as the time progresses, as we go in.
Sir, I don't know what has happened finally, but in converters, sir, there is a big debate whether it should be zero frequency conversion or infinity frequency conversion.
Well, that we do not go into that debate, that is left to power electronics classes.
Sir, what has been finally adopted?
No, that I will not talk on that, because this debate will, because we have only 6 lectures left and we have miles to go. We have to cover AGC, otherwise you will be left, because Professor Bhatti used to cover half the classes in AGC only, and I have not yet done AGC at all. Suddenly I realized I have to do AGC. So, then there is a transmission line or cable, this is back to back, that means length is almost 0, and then there is a converter station. Where do you use this back to back? Wherever there are two systems which have different frequencies, which are not in talking terms. You need a mediator, like Pakistan always says we need a mediator to talk to India. So, since there is for France 60 hertz, England 50 hertz, and if you want to interconnect this France and England, the best thing is HVDC link, which is called asynchronous link. So, this back to back connection is nothing but making two non-talking partners talk, and then converting station and back to AC, whatever frequency you want. And if the frequency is same, then of course there is no problem, and still you can have it, and there are certain advantages of not getting synchronization, etc., etc. Now, what do we need? We need two series connected 6 pulse converters, which is 12 pulse bridge consisting of valves and converter transformers. The valves convert AC to DC. What do you need? A smoothing reactor? You should show the figure. There is a smoothing reactor shown here. This smoothing reactor is required in DC circuit to reduce harmonic currents in DC line. In fact, there is a separate book on power system harmonics, and you should read it. It's by Neville Watson. He's a good friend of mine. I visited him for a month in University of Christchurch, New Zealand. He has several books, and all his books are now available in India in cheap edition, on dynamics, on harmonics, in power system analysis, and so on. Arilaga has a HVDC book also. Even Hingorani has a HVDC book. Kimbark has a HVDC book, and our own Indian book Padiyar, that's an HVDC, exclusively on HVDC, and chapter is given by many books. Now, the valves convert AC to DC. A smoothing reactor in DC circuit reduces harmonic currents in DC line and possible transient overcurrents. So, smoothing reactor, as the name itself indicates, smoothens out several things. It makes your life easy. Filters are used to take care of harmonics. Why these power electronics have created, why power quality has emerged as a major player, major topic for PhD, MTech, BTech, because of this power electronics, the problems. Otherwise, 30 years back, there was no harmonics. AC to DC converter station is called rectifier. Again back to AC will be your
at the receiving end.
DC to AC inverter. How do you convert and control these things? By varying the firing angle. All thyristors operation control can be done by, and you can have a big control circuits which will control this firing angle, microprocessor based, computer based, intelligent control, or whatever what you have. All those sorts of things. There are big controllers, sliding mode controller, variable structure controller, and there is a whole lot of host of controllers. DC output voltage can be controlled between two limits, positive and negative. That's why we always specify plus minus 500 kV, plus minus 600 kV, and so on. Maximum DC voltage will be available when alpha is equal to 0 degree. For rectifier operation, alpha varies from 0 to 90. For inverter operation, it varies from 90 to 180 degrees. An extinction angle is nothing but 180 minus complement of alpha. That all these things you know because you know better power electronics. I have never studied power electronics. Harmonics. AC, any AC DC converter. See, the ADC, AC to DC, DC to AC converter has become an important ingredient of so many circuits in electrical engineering. Is a source of harmonics. Don't think only on AC side, AC, DC both. So it spoils uniformly. There is a socialism there. It doesn't spare any particular variety of circuit. Shunt filters used to avoid bad effects of harmonics on AC side. At fundamental frequency, the filters act as a shunt capacitors. That's why any capacitor can act as a filter. In SVS, you might have studied that while studying static VAR control. Supplying reactive power to the converter.
Both functions.
So you can use these capacitors. As I told you, we need to supply reactive power in any HVDC circuit. A smoothing reactor is installed to limit harmonics on the DC side. This we have already is restated here, reiterated here, so that you don't forget. Now let us find out what are the various reactive power demand which are additional here besides AC requirements. So, we not only HVDC line cannot carry any reactive power, there is a additional load burden in HVDC circuit of reactive power requirement. At converter stations, due to the control of HVDC converter alpha and gamma, which introduces a phase shift between the fundamentals of AC current and voltage. You must have read lot about commutation, linear commutation, commutationless motors and so on. Commutation is a big issue in power electronics. The commutation process in which the DC current is commuted from one wall to another and which introduces further phase shift.
That is why thyristors are very bad.
Yeah?
That is why thyristors are very bad.
That's right. In fact, we are shifting to these
IGBTs
transistors and
IGBTs and MOSFETs.
IGBTs, MOSFETs,
But MOSFETs
because
have
of
got charge problem.
see, there is always plus and minus in life. I have been telling you, you won't get anything perfect in this world. Even gods were not perfect. I have told you several times. So, there are problems. You have to see which particular thing gets best fitted in a given situation. Even if you want to cure your health, you have to take some medicines, which also have a short side effects, but you have to take a medicine. Converter transformers also consume reactive power. So, Q demand is roughly 50 to 60% of total transmitted real power. This is the brief story about reactive power requirement in HVDC line. Now, naturally, when you have a requirement, you have to worry about its supply. If you need 1000 rupees, you will have several options. You ask a friend if a scholarship is due, or look towards your parents. So, you have to get 1000 rupees. There are several ways, or do extra labor, which in India no student does. In abroad, every student earns his own money while studying, earning while learning. It is a slogan in India, it is a reality in abroad. So, as I said, the automatic next topic should be how do we get those 50 to 60% of reactive power of total active power. First, AC filters. Second, shunt compensators or capacitors. Then, excessive reactive power from AC network. Static compensators, this is for fast voltage regulation, SVS. You are all familiar with SVS or SVC, static var controller or a static var system. And synchronous condenser. We have also done this topic in chapter 5, if you recall, and we compared static compensators versus dynamic compensators, their plus and minus points and so on. Synchronous condensers are recommended especially if AC's network is weak. That means they don't supply much of reactive power. While choosing reactive power generation equipment, one must consider, in fact, this sentence is valid for anything in life. you have to consider economic as well as technical aspects. Suppose you have to take a treatment, which doctor you will go? Not cheapest. You have to also see he won't make you die also. So, he should have some reputation, he should have some history of curing some people. Otherwise, why should you go just because he is free or he is available freely, if not free. So, economic and technical aspects both. In what proportion, again it depends on, this is a continuous optimization problem you are solving in life all the time. That is how much economy is important and how much requirement technical. In my mind, technical requirement should get a preference over economical requirement. But at times if you do not have money, what can you do? Principles of HVDC control. Here let me tell you one more thing. Because of HVDC, whole power system dynamics is changed, whole power system control is changed, whole power system analysis course is changed. How? Can you explain me why it has happened? Just one topic has changed all these textbooks. They have forced them to, because the modeling has changed. What should be that bus where HVDC is connected? How do you model that? And the best book which talks about this is Arrillaga. He is a Spanish chap and settled in New Zealand.
Height of the HVDC wires
Height of the
HVDC wires
what happened to that?
is taken into account.
Yes, everything has to be taken into account. But
Means wide it must be.
huh?
Wide is kept low. Height.
No, that as I told you, that is a different mechanical considerations, the sag and tension, the chapter we did. Why do you think we have done all those chapters? Briefly, because they affect design. So, how much should be the clearance? What is the field being produced by DC? How it is different than AC? How what area it affects? How far should be the nearest building? If you see, if you go to that Shivalik or Vindhyachal behind, now we are building a boys hostel 800. Have you seen that? Do you go for evening walk, morning walk,
Sir, it's on
or
the-
no walk for you?
That the other gate, sir. That side gate.
Which other gate? This gate.
No,
Behind
the other
behind
gate.
Vindhyachal there is no gate.
Sir, it was
I am
like
talking
a-
about mini campus. So, if you go there, there is certain minimum clearance between the existing houses and boys hostel. We do not want you to just see what is happening in these quarters. It should not be so dangerously close. So, there has to be minimum clearance, or your windows should not open towards their windows. These are again a consideration, may not be technical, but these are practical considerations. Anyway, let us come to the why it has made people write different editions of the books when HVDC has come back. The load flow is changed. The AC/DC load flow is entirely different topic. What should be the bus? What should be specified? What should not be specified? Anyway, we will see it when we arrive at the bridge. We will cross the bridge when we will arrive at it, as they say in English. One of the most important aspects of HVDC systems is its fast and stable controllability, which property is not available in AC. The controls are fast and easy and stable. There is no point in having unstable control. In DC transmission, the transmitted power is proportional to difference in voltages at the two ends. If you want to call it sending end and receiving end, you can call it. and hence can be controlled by these two voltages, which are DC voltages. Current can only flow, this is not I can only flow, this is current. Current can only flow, so that there is no misunderstanding. In one direction. See, I am in habit of writing shorthand. In one direction for a given setting. You can't have a current flow in a different direction. If you want to have, then again you have to change the voltages. Yes, any control, which is easier in AC to change the direction.
In alpha, it is much easier in HVDC, sir. Just by changing the alpha, we can change whether it is received or transmitted. Both direction it can flow.
How about you have to change alpha?
It is very easy to change, sir, alpha.
Easy, but otherwise if you do not change, then it can flow only in one direction.
Yes, sir.
Nowadays alpha is not used, only PWM is used.
Pulse width modulation.
Yes, sir.
Power is transported from rectifier or transmitted from rectifier to inverter, and by altering the voltages.
The power flow direction is reversed.
The power flow direction can be reversed.
Yes.
Okay,
Very easy.
white touch alpha and gamma. So we can just change the
Alpha control.
voltages. Now this figure tells you whatever I have been talking in last 2 minutes.
Modeling.
Here is a rectifier station, here is a inverter.
DC voltage.
Rectifier converts AC to DC,
DC to AC.
and inverter converts DC back to AC, because in reality the generation continues to be AC and distribution circuits continues to be AC. There are hardly any DC loads, there are hardly any DC distribution system in the world. So only it is transmission sector which has gone
HVDC.
primarily DC mode, not distribution nor generation. Now these are the your converting stations. This ID is a DC current, R is the total resistance. I included, lumped all the resistances here. Now there is no short line, no middle, there is only long line here, 2000 kilometers, or there will be zero length line for back to back. So there are only two applications. So nobody will build for short line a DC because it is very costly. VD1 and VD2
DC voltage.
are the DC voltages at station 1 and station 2. Receiving end, sending end also can be used as an R. Inverter station is so controlled, the system DC voltage is fixed and fixed relation to VD1. You can always use transformer taps to take care of any small variations, slow variations. The transformers are still there. Converter transformers. ID can be controlled by controlling VD1 and VD2. Again, reiteration of the same statement which we have done. ID is equal to VD1 minus VD2 by R. This is simplest. There is no cosine, no sine, no phase shift, nothing is there. If you increase ID, obviously power will also increase. As simple as that. This again in a very shortcut notation. I have explained, if you increase ID, results in increase in PD. For God's sake, don't use such notations in any other subjects which teachers won't follow. So you can only use it for those people who follow it, who understand it. Otherwise, say I have not understood it. What you have written this? He will say that you have cancelled it. and sent it somewhere else. What is PR? Receiving end power. VD1 minus VD2 upon R into VD2, current into the voltage at that point. This is current in a voltage at that point. VD1 and VD2 are also given in terms of alphas and gammas, which you have been talking so far. 3 root 2 VLR, VLI, alpha, gamma, ID, XCR and XCI. What is N here? N is the number of series connected bridges.
6 pulse bridge.
Right, whatever it is. You know power electronics, as I told you, so I am not going to go into power electronics. I will only explain you the power system part of it. VLR and VLI are line to line AC voltages at the rectifier and inverter bridges. R stands for rectifier, I stands for inverter, L stands for line, V stands for voltage. The XCR and XCI, these are commutation reactances at rectifier and inverter end respectively. DC power is proportional to, again I am reiterating, two voltages VD1 and VD2, which in turn are proportional to alpha and gamma. Just now you said few minutes back. These are converter control angles, and their operating range is given by alpha min is 5 degree, alpha max is 15 plus minus 3 degrees, and gamma min is around 15 degrees. This is from experience. In fact, you can solve optimization problem and get these values depending on what is your objective function. The objective function changes, the values will change. The constraints change, the values will change. So, values, final optimum values always are dependent on what you want. If you want to save money, the optimum way is take 620, 10 rupee, you reach station. But if you have lot of money, then auto. If you have still lot of money, taxi. If you have no money, lift. Minimize reactive power requirement at the terminals reduces losses.
No sir, VD if increases then Q will decrease.
No, sorry. You want to minimize the Q again I repeat, you want to minimize Q requirement. Anybody will like to minimize any requirement except the money. You want to have more and more money, more and more comfort, but anything on expense side you want to minimize. Now, how do you achieve this minimization? See, it is very complicated way it is written. You have to increase VD or reduce alpha. This will reduce losses. If losses are reduced, naturally your Q requirement is also, because losses are also to be provided, they won't be provided by God, and that is why in load flow slack bus is not to be specified till the end, because if that is the job of slack bus is to provide losses, and losses are not known till the end. So, that is why in slack bus you do not specify P's and Q's, you only specify V and delta. Now, we come to economic considerations, which are very important. Let us compare AC line with DC line. These are the only two comparisons. To have the valid comparison, all other conditions remaining same. This is the line we always use. What are the conditions here? Employing same number of conductors and insulators. Let us compare the power per conductor on the two lines. Let us assume we have current DC is equal to AC RMS. and VDC is of course equal to root 2 times VAC. VAC is RMS. If you want peak value, you have to multiply by root 2, and peak value can be your DC value. So, DC power per conductor is how much? Very easy, just multiply voltage and current, VDC into IDC, which is equal to PDC. PAC is, as all of you know since your childhood, VAC into IAC into cosine phi. The first mantra which is given in first semester by Thareja. VAC into IAC into cosine phi. Take anything you want to compare, the easiest thing is take a ratio of them. So, PADC upon PAC, substitute the values, we have just obtained them, VDC into IDC upon VAC IAC cosine phi, we are left with root 2 upon cosine phi. So, root 2 is always more than 1 because it is 1.41, whereas cosine phi is always less than 1. At the most, worst case or best case, it will be 1. So, this ratio is bound to be always more than
1.4.
It can be more than 1.4.
Always more than 1.41.
Actually, you are saying that. All right. Always more than root 2. Because worst case it will be divided by 1, and rest of the times it will be less than 1. Let us hope it will not be 0. So, otherwise it will be infinity. Cosine phi will never be 0. Never be 0. That means the angle should be 90 degrees.
No, only pure inductive. Only
Pure inductive transmission line.
There is nothing like pure inductance. Some resistance is always attached to it. That is only in theory, pure inductor. Taking cosine phi as 0.945, which is a normal value in Western countries, not in Indian context. But anyway, this is just an example. We get a nice figure. Actually, I work backwards.
Yeah, 1.5.
See, I told you the secret of how writing books. So, this figure should come neat, 1.5. So, it registers in student mind. Oh, dead ho jata hai, you know, 50% more power. Suppose it is 1.61, you will say, what is this figure, 1.61? So, I have chosen backwards and got the value of cosine phi as 0.945. Compare 3-phase and 3-conductor, this is an assignment for you. Similarly, as I have gone for this, you compare 3-phase, this is a take-home assignment. In USA it is called take-home assignment. Here it has no meaning because everybody will join together and solve it. So, that will not serve any purpose. In fact, they give marks also on take-home assignment, which in India we can't do because we will just consult each other and solve. So, 3-phase 3-conductor AC line with a bipolar 2-conductor DC line. The answer I am giving you, both lines carry the same power. So, they are exactly equivalent. So, this is a home assignment to you, and do it and see whether you get this answer or not. Today I have to go early, there is a meeting. So, still 2 more slides. DC line is however simple, anybody will say that, cheaper. Why? Only 2 conductors instead of 3.
But it is a must to have a neutral, sir, in HVDC, because that to inverter.
But neutral conductor is always cheaper than
but it is
the
always
live
conductors in HVDC.
the line conductors. In any case, this statement is true that DC is cheaper as compared to AC as far as conductor cost is concerned. Further, overhead line requires only 2/3 as many insulators. Towers are simpler, cheaper, narrower, and it results in a narrower right of way, which is a very big issue nowadays in many countries. Both lines have the same power loss per conductor. So, PL is also less, that is the total loss, real power loss. DC cables are always better than AC. Yes, yes, but costly at the same time. So, this is a brief comparison.
BDV of DC is BDV of air for DC is less than BDV of air for AC.
What is BDV?
Breakdown voltage.
Oh, breakdown voltage, that is a separate category.
Reliability is also more, sir.
There are so many. I told you I am going to talk. It's not the end of HVDC. We'll have one more lecture, and the remaining points we'll talk on Tuesday. What are HVDC applications? One applications I have told you so far. We'll reiterate here. Following modes of implementing a DC link in a predominant AC systems may be used. As I told you, most of the system continue to be in the world, not in India, AC, and will continue to be so in near future or foreseeable future. Why near? Unless until some breakthrough somewhere happens, which we don't know. Interconnection of systems of the same frequency through a zero length. This next is 0. DC link, and we have already talked about it, back to back connection. This does not require any DC transmission line. In fact, both the converting stations are housed in the same building. If you go to Satpura HVDC station, if at all you happen to go sometime, you will see that they are all both the converting, or Chandrapur while going to Madras after Nagpur, around 3 hours, after 3 hours. So,
NTPC Dadri is also.
you can go to Dadri also. Dadri is very close to Delhi. Does not require any DC transmission line, and AC lines terminate on rectifier and inverter stations housed in the same building. Second important HVDC application is transmission of bulk power. As I told you, north east to south, that is going to be the biggest HVDC line perhaps in the world. 2000 kilometers. Many countries will not have a length of 2000 kilometers, barring Australia, US and Canada if you go east west, not north south. North south, only India or China or USSR will have 2000 kilometers. US perhaps will have. US will have. Australia will have, of course. Australia is twice the size of India. 2 India makes 1 Australia, area wise. Population wise, 1 Delhi is more than Australia. Any difficulty so far? In case if there is no difficulty,
Sir, when the same frequency, then we do back to back, or when
we can do for different frequency as well. As I said, France and England.
So then why for same frequency?
Same frequency also we do for avoiding any synchronization problems.
To synchronize.
So there is no synchronization required.
So this for just for synchronization.
And to isolate if you want.
Isolate more.
It's not just one thing.
Yes, sir.
See, that's why certain things you should also think yourself. You are a master's graduate, students. You have come of age. In fact, any one of you could have been teacher anywhere.